Our second speaker will be Paulo Resch from University UFRGS from Brazil University and Università di Toronto in Italy. So it will mainly talk about the radiation effects on autonomous vehicles. So Paulo, I think the floor is now yours. We can see your screen.
Okay, can you hear me also?
Yes.
Okay, thanks a lot. Thanks Manon and Carlo, and Rubens and Igor for taking care of this webinar. I think it's very important that we don't forget about thermoneutrons. When I was invited to give this talk, I was very happy to share my experience. Then I realized that I was about to talk after Robert Bauman, and I got scared because how can you beat such a very good talk with a lot of insights. So a disclaimer, this talk is from an engineer, and I will be an engineer, so I will talk about what we have observed, give you some numbers, and try to understand basically the fundamental question, which is, I will learn the lesson. So we know that when boron 10 is there, the error rate can be higher. Are we considering that or not in our computing devices? Mainly for two applications, supercomputers, that because of their large scale, they can have reliability problems, and autonomous vehicles that we don't want them to fail. Before starting, some of the sponsors need to acknowledge that basically made everything that you will see possible. The Los Alamos National Labs through the Rosen Scholar Fellowship gave me beam time and support. The ISIS facility, so Carlo and Chris, and ILL, so Manon and RADNEXT, so Ruben, for the beam time and research grants. Let me stress out that participating to RADNEXT is a wonderful opportunity to perform some radiation experiments. So if you want to try something, apply by the end of the month. I also need to acknowledge NVIDIA that provide us with some GPUs, and the European Commission for my Marie Curie project period. So as we have learned, the reliability problem in the terrestrial environment comes from the galactic cosmic ray that hit the atmosphere and generate a cascade of particles that reach ground. And we should mainly consider neutrons, the high energy ones. As Robert mentioned, at sea level, we are close to 13 neutrons per square centimeter per hour. These are a huge problem for electronic devices. And since they are highly energetic neutrons, there is little you can do to protect your device from them. So when we talk about high energy neutrons problems at sea level, we are talking about something that we can't avoid. So there is not an easy solution. We need to deal with them, either with software hardening, with hardware duplication, or simply accepting the fact that our device will eventually fail. The other mechanism that we are discussing today are thermal neutrons. So neutrons of low energy that are normally present, and as we have learned, they can be a problem, mainly if your device has some boron 10 in the manufacturing process. If you remove boron 10, or if you use a purified boron 10, then the thermal neutrons basically becomes a little problem. The problem is that we need boron for manufacturing our chip devices. And since purifying boron is very expensive, commercial devices typically contains or might contain boron 10. The interesting part is that for us mere mortals, the customers of these devices, we have no idea of how much boron 10 is in the chip that we are buying. So it's hard for us to understand whether the commercial device that we are buying is or not sensitive to thermal neutrons. What is happening in the market is that we have different applications with different reliability requirements that goes from good for the consumer electronics. So basically, what we just need there is that the user is happy, sufficiently happy. And if something happens, so if there's a failure, somebody else is blamed, not the manufacturer of the device, which is normally what happens. So when our mobile phone crashes, we normally blame Microsoft or Apple. We don't think that the problem is in the silicon. When we move to HPC and data centers, then we need a higher reliability requirement because of the scale of the machine and the length of the simulations that can last for weeks. So if you have an error during a simulation that lasts for a week, you need to repeat it, and that is very costly. And then lately, we need to consider automotive applications for the self-driving cars, for instance, and there the reliability requirement is extremely high. And we have a lot of devices out there. We have ARM embedded system, we have CPUs, coprocessor, GPUs, FPGA system on chips. There's a plethora of things that you can use. And what we are seeing now in the market is that the same device is used in application with different reliability requirements. ARM processor were very popular for mobile phones, but now they are using HPC. So the new clusters in Los Alamos, for instance, is designed with ARM processors, and ARM has a line dedicated to autonomous vehicles. The same is for GPUs, for instance. The GPUs are the devices that you wanted where you were a teenager for gaming. And today it's used for accelerating graphics, but GPUs are used in many supercomputers, and obviously to accelerate neural networks for autonomous vehicles. So the point is, these devices were designed maybe for consumer applications. So they are cheap, they are fast, they are very efficient. And now we want to put them in an application that has a much higher reliability requirement. Can we really do that? I mean, if the device was not designed to be highly reliable, then it might contain boron, for instance, or have other problems. So the message here is that we cannot assume that commercial devices are immune to thermal neutrons. And the answers that we want to work on are the following. So how much are these commercial devices sensitive to thermal neutrons? And should we consider thermal neutrons contribution to the device error rate, or is it negligible? And finally, do we need to care about the environment in which these devices are employed? So will the error rate be influenced by the environment, like if it is raining or not? To try to answer to these questions, this is the technical outline of the talk. I will give you a very brief introduction of neutron effects in modern computing devices. For then, let you see how we design and the experimental setup and perform the experiments. I will show you some data on dynamic memories, and then I will discuss about the difference between thermal and high energy neutrons cross-section. So we will compare the error rate of a device caused by thermal and high energy neutrons. I will give you a couple of words by the last experiments we performed on Google sensor processing units, and then I will conclude. So we know what happens, right? So what happens is that when the neutron hit the electronic device, it basically flipped some bit in the memories without giving you any notice. So these are called soft errors because they are not permanently damaged, but the information that you stored is corrupted. And the same can happen in logic, okay? So you are executing an operation, there comes the neutron, and your result is wrong. It is wrong in a silent manner, right? So you do not know that the output is wrong. When we deal with modern computing architectures, there are a lot of places that can be corrupted, so memories or logic cores. And since these devices are typically very big and include a lot of resources and a lot of parallel processes, you can also hit some critical resources like the scheduler or the caches. And this single fault can actually impact the execution of multiple parallel threads. And the same can happen at a larger scale when you hit the big scheduler of the system. So the way the fault propagates from the transistors till the output of the application is much more complex and needs to be deeply studied. When you have the soft errors, if you hit an operating system process or the control flow of your application, you can expect an application crash or a device reboot. I'm sure you're all very familiar with these messages. Well, don't always blame Microsoft or Apple, because it could be that a neutron hit your device. And again, if you blame the operating system, then you're making the chip manufacturer very, very happy. When we talk about neutron effects, right, it's hard to convince people that these are important. And I normally show to my students this image that I took from the series Chernobyl, in which, if you've seen the series, of if you know how they try to clean the roof of the reactor after the explosion, they try to use a robot called Joker that, because of radiation, it lasted just a few seconds, then it crashed, and that was the end of the experiment. While humans were safe for minutes on the same rooftop. So while we think the neutrons are bad for us, remember that they are much worse for the electronic. But you don't have only crash, right? If the error happened in the data path or during the execution of your application, you will see the output of the application coming, but this output is wrong. And again, it is wrong in a silent way, so there is no indication that the error is there. So these are all outputs for the PC is the correct output, but it's clearly wrong to us. This is an example of a soft error on HPC simulation. They were simulating weather forecasting. This cloud over here, this gray cloud, this was actually at the end of the simulation. They found out that this is not really a cloud, but it was a sea salt aerosol. So basically, there was more salt in this cloud than there is in the whole Earth. And then going back to the simulation, they found out the point when the first error happened, and then propagated the simulation output. And I'm stressing HPC and these big servers because, again, because of their size, right? So it is very likely for a particle to corrupt at least one of the nodes of the HPC. This was the case, for instance, of the Big Mac supercomputer that was designed using a 1100 Apple Power Mac G5. So these were very efficient CPUs for consumer electronics. So they had nothing to protect them from radiation, not even ECC in the main memories. Well, basically, the supercomputer couldn't even boot because of the failure rate. So the operating system got corrupted before loading it. So it was basically a useless supercomputer. And other examples like Jaguar and ASCII-Q, both at the Los Alamos National Labs. Jaguar had 350 ECC errors per minute, while ASCII-Q couldn't run for more than 1 hour without a crash. Then they tried to shield it, and the run was of 6 hours, and then the system crashed. This system takes tens of minutes to boot. So every 1 hour or 6 hours, you need to wait 20 minutes for the system to boot. So this was not obviously ideal. And there are a lot of examples of neutron-induced effects. I will just comment on one that you probably already know, which is the Brussels case, when Maria van der Vogel gained 4,096 extra votes because of a neutron error. And I'm commenting on this because next week we have election in Italy and in a couple of weeks in Brazil. And I wish I could blame the neutrons for the outcome. But obviously the other application that we are all interested in are self-driving cars, and it had already happened back in 2007 that neutron strike corrupts the electronic of a car. It was obviously not a self-driven car, but it was a normal cruise control causing death. The new trend is the self-driving cars, which are much more complex, as they had a lot of electronics. And the interesting aspect of self-driving cars is that to enable the system to detect the objects in real time, so you don't have time to wait, but you need to detect the objects in real time. So it's a pretty complex task. People are using commercial GPUs or big parallel devices because they are cheap, they are efficient, they are effective, but who knows, maybe they have boron 10. If you want to put that device on a car, any kind of electronic device, mainly on a high risk system, like a self-driving car one, your error rate must be lower than 10 feet. A feet means an error every 10 to the 9th hour of operations. Okay, so it seems like a big number, but if you multiply by the millions of cars that are in the world, that basically means hundreds of errors per day. The question is, should we also consider thermal neutrons contribution to this fit rate? And we try to see how we can do it. We have these commercial devices, we have the critical applications. We want to see if they are sensitive to thermal neutrons, so we perform radiation experiments. So this is an example of an experimental setup. I need to give credits to Fernando, not just for designing the pictures, but for actually designing the experiment itself. So what you basically do is to align the device under test with the neutron beam. This is ROTAX at ISIS in the UK. It's a thermal neutron facility. So you have the beam that hit your device under test. In this case, this is a GPU by NVIDIA. And then we control the device using a closed network, basically. So from the outside through Ethernet, we can control it. And what we basically do is, while the device is radiated, we load the input, we execute the code, and then we compare the output with the expected value, and eventually we count standard data corruption in the output or a DOE. And this process needs to be repeated forever until you get a sufficient data. Very important aspect, the code execution is what you're more interested in. This must take 90% or more of the whole cycle. Otherwise, you are not testing your code, but you are testing the loading or the input or the comparison of the output with the expected one. And finally, we also include a power switch, which is able to automatically power cycle the DOT if that becomes unresponsible. This is fundamental when you test with neutrons, because the error rate normally is low and you want to test 24 hours, so also during the night, and you really do not want to see that your device got stuck 5 minutes after you left for go to sleep. And that happened a lot of times in my experience. So it is also very important to have a fully automatic system. What do you do when you do these kind of experiments? Well, you want to see how sensitive the device is, right? So you need to count how many errors you observed and divide by the number of particles that hit your device. So obviously your system is the one that should be able to count the number of observed errors. The fluence is normally given by the facility scientist, so Manon, Carlo, basically. Your responsibility is to actually ensure that you are considering the effective fluence. So the fluence that hit your device while you execute your code, not while you are setting up the device or while the device is being rebooted. So you must be sure that you are counting the neutrons when you are actually executing your code. When you do this operation, you divide these two values, you have the cross section, which is measured in square centimeters for traditional reasons. But just take the cross section as the probability for one impinging particle to generate an error. That can be either an SDC or a DOE or what you actually define as an error. And the cross section is very important, because if you multiply it by the natural flux of your device, then you will have your error rate. So that is why the cross section is so fundamental. These are a couple of images. This is TENIS in France. So I asked Manon the beam time there. This is ROTAX, and we also tested at EMMA at ISIS. I put the picture of ROTAX because the picture looks much cooler than the EMMA one, but EMMA is now the facility, if I'm not mistaken, that we normally use for thermal neutrons. This is this we were testing the TPU of Google, and this is the Titan V of NVIDIA. Manon and Carlo designed this wonderful spectrum of energies of the beam. As you can see, the energy drops very quickly. So these facilities basically focus on low energy thermal neutrons, both of them. There is a big difference, which is the flux. So we go from 10 to the 9th neutrons per centimeter per second at TENIS to about 2 10 to the 5 in ROTAX, at 2 10 to the 6 at EMA. So the difference is that the error rate can be too high in TENIS or too low in EMA ROTAX. So the point is that you do not know the error rate because you don't know how much boron there is in your device. So you need to calibrate the experiment and the setup online while you test it. At TENIS, for instance, Manon was very smart in helping us in try to reduce the error rate because it was too high. And having a too high error rate is not good because you do not know how many neutrons hit the device while you compute your application. So you might end up having multiple neutrons generating multiple errors in the same execution. And that is obviously something you will never see with the natural flux. So at TENIS, you can actually move your device and you can move it to the edge of the beam. This is the intensity of the flux. So you start by testing the device in the very high intensity, then you see that you have too many errors and you start to move it to the right. As you move to the right, you basically reduce the intensity of the beam. So you can go down by a couple of orders of magnitude. And we basically tested and profiled the whole beam with the TPU, and we actually end up having good data. Some data, some results, we tested DDR memories. So the DDR are the main memory of your motherboard. Our first experiment on thermal neutrons was on DDR3 and 4 because they are very easy to test their memory. So we load a known pattern like A or 5.5, and then we continuously read it and check for bit flips. The beam spot was able to cover just half of the memory. So then we normalize the error rate by the number of exposed bits. These are some of the results. So this is the cross section per gigabyte in square centimeter for the DDR3 on the left and DDR4 on the right. Please mind that the scale is different. So the DDR3 is 1 order of magnitude more or less more likely to be corrupted by thermal neutrons than the DDR4. Mind also the difference between the fault model. So the DDR3 basically only experienced transitions from 1 to 0, and the DDR4 from 0 to 1. Other interesting results that we observed is that all the soft errors that we have observed, so errors in the memory, not SAFI. SAFI means that the device needs to be rebooted. It was completely unable to functioning. But all the errors that we have seen in the memory array were single bit flip. So basically, they are all correctable with ECC. What was very concerning was that most of the errors were not transient, but they were intermittent or permanent. Intermittent means that the error appears every now and then in the same position, even if the beam was off. That is probably because we were stressing the memory or we were increasing the temperature. Permanent means that that bit flip was always there, no matter if the beam was on or off. And most of the thermal neutron-induced errors were actually not transient, so the device was permanently damaged. Then we tried to see on the computing device if thermal neutrons are a problem compared to high-energy neutrons or not. As Robert mentioned, it would be very good to have a facility that delivers both thermal and high-energy neutrons where ISIS does so. You have cheap IR, which is the high-energy neutron, the atmospheric neutron beamline. It is very cool because you can align different boards and test all of them. And then you have ROTAX and EMMA, where you can test with thermal neutrons. And you have also NILE, which is the new facility that Carlo designed to test monoenergetic neutrons. The cool thing is that we were testing with high-energy neutrons. Then we take the same board with the same setup, move it to the other room, and test it at ROTAX. So we were testing the same DOT, the same code, the same input, the same supporting hardware. So it was exactly the same thing. And obviously, this is a different kind of neutrons delivered at cheap IR on the right and ROTAX on the left. As you can see, ROTAX is mainly thermals and cheap IR is mainly high energy neutrons. We tested different devices. We had a lot of beam time. I'm talking about, I think it was 28 days there. We tested Xilinx FPGAs, Intel Xeon Phis, 3 different NVIDIA GPUs, the K20, the Titan X, and the Titan V, and the embedded APU of AMD. As you can see, we had different kind of device, programmable logic, accelerators, GPUs, and normal CPUs with different technologies, from planar CMOS to Intel 3-gate and FinFET. So again, what we wanted to do is to really have a broader review of the thermal neutrons problem. And we run different kind of codes, from particle simulation to matrix multiplication, convolution, neural networks, HPC simulations, again, to use the device with the application it is designed for. These are the results. So here I'm not plotting the cross-section of thermals or of high energy neutrons. I'm plotting the ratio between them. So here I'm plotting the ratio between the high energy neutrons cross-section and the thermal neutrons cross-section. So as you move to the right, so the longer the lines that you see, it means that the cross-section for high energy neutrons is higher than the cross-section of thermals, which is a good indication that the manufacturing process is better, because thermal neutrons are less likely to generate a fault than high energy neutrons. As you can see, we test the different devices. We test the AMD stressing just the CPU, just the GPU, or both of them. We test the 3 different NVIDIA GPUs. We test the Xeon Phi, and we test the Xilinx FPGAs with different codes. What we have observed is that all these devices are sensitive to thermals. And the sensitivity to thermals depends on the device, not surprisingly. For instance, for the Xeon Phis, on the average, the high energy neutron cross-section is 10 times higher the cross-section of thermals, which is, again, an indication of a good manufacturing process. So these devices are pretty low thermal neutron cross-section compared to high energy neutrons. For the GPUs, the situation is slightly different. So the high energy neutron cross-section is 2.5 times bigger than the thermals. So there is some problem there. Another interesting aspect that we still need to investigate further, because it was quite surprising, is that the comparison between the thermal neutron and high energy neutrons cross-section depends on the codes that is being executed. Probably this means that the memory and the logic has a different response to thermals compared to high energy. So to give you an example, on the same device, which is the AMD APU, the SC code has a 2.5 times higher cross-section for high energy compared to thermals, while another code, BFS, has a 13 times higher cross-section. So there is some mechanism there that we need to investigate further. So the cross-section is one piece of the game, right? So the cross-section is the probability for one neutron to generate an error, but you need to multiply it for the natural flux in which your device operates to have the actual effect of thermals in your application. While for high energy neutron, we normally use 13 neutrons per centimeter per hour, although that is a simplification. For the thermal neutrons, that is not easy to be predicted because it can be influenced by a lot of factors. What we did was to try to understand the impact of the environment on thermal neutrons. So we simulate the different environments, concrete walls, water, for instance, the cooling system of your supercomputer, the fuel of the car, and all of these actually increase the flux of thermals. So this is a kind of an example of the spectrum energies of neutrons for the flux. For the concrete wall in green and red, then the water in blue, and then the other mechanisms. In particular, we have looked at the supercomputers in Los Alamos that are water cooled. So this is a picture of the water cooling pipelines. And we use a thermal neutron detector designed by Steve Wender, and we place far from the water cooling system, and then we put it close to the water cooling system. And as you can see, we had an increase of about 25% of the neutron counts, meaning that the water pipes and the cooling system of the supercomputer can be pretty effective in increasing the thermal neutron rate. We simulate the effect of water in the supercomputer rack. So imagine these are all pieces of a supercomputer. Each line of these are basically a node, and they are connected in clusters. And the water goes from the bottom to up. And as you can see, the closer you are to the bottom, to the water, the higher the flux of thermal neutrons. And the true thermal neutron flux, according to our measurements, can be increased from 40 to 80% because of the water-cooled systems. So we have tried to understand how much the thermal neutron rate the thermal neutrons can contribute to the overall device fit rate. So here I'm showing the contribution to the fit rate for 3 different devices: the K20, the Titan X of NVIDIA, and the Xeon Phi of Intel. For the high energy neutrons in red and thermal neutrons in blue. As you can see, for some specific applications, like when you have water and concrete close to the device, the fit rate can be increased of up to 40% because of the water cooling system of your application. So it's definitely not a negligible amount of errors that can come from thermal neutrons. This is also pretty funny if you consider that most, if not all, of the servers in the world are very close to water, and mainly also close to the ice on top to ease the cooling. So there is also a Microsoft server that is actually underwater, so that can be either good or bad for thermal neutrons. I mean, it depends on how deep the device is under the water. And also, this is also interesting for autonomous vehicles, right? So what if, I mean, if you're riding the Italian ways with the sunny weather, then you are fine. But if you move to the UK and it rains, maybe your car can have a higher fit rate because of the moderation of neutrons in the water. So those are all things that needs to be considered. Finally, the last thing I'm showing you is the latest experiments we performed at ILL and EMMA using the Google TPU. It is a very efficient accelerator for neural networks. So basically, it simply executes convolution in a very effective way. And convolution is the operation that you need to perform to detect and classify object in a scene. We run the TPU, which is basically a systolic array that receive feature maps in the input and perform all the convolution in a systolic array manner. And basically, we wanted to see how many errors thermal neutrons can induce to this kind of device, and if these errors is critical. So we are misclassifying or misdetecting objects. These are some of the results. So these are the high energy neutron cross section. This is the thermal neutron cross section for all the configuration that we tested. The scale is the same, as you can see, but the cross section to thermals of the device is much lower. So it's about 2.5. While for the high energy, it goes from 50 to 60. So more or less, we can tell that the TPU is quite a good device, and the thermal neutrons cross-section is 1 order of magnitude lower than the high energy neutron one. This leads me to the conclusions. So we need to think and consider that commercial devices might still include boron 10 in the manufacturing process. I mean, money is quite a good variable for the industry. So we actually need thermal neutron experiments to evaluate the contribution of thermal neutrons to the device error rate. So take advantage of RADNEXT proposal and ask for beam time, and be curious to see if your device is well designed or well produced or not. We have saw an application-dependent response to thermal and high energy neutron. which basically means that the fault model depends on neutron energy. We are still not sure if that is because of the implementation of the transistors, or because of the architecture, or because of the way the fault propagates in the software. So that needs to be investigated further. When you test with thermal neutrons, then you will need to measure the flux of thermal neutron in your application, and that is not very easy. But for sure, I hope that we have convinced you that thermal neutron needs to be considered in the qualification process of the device, mainly if you buy the device on the shelves. So there is no indication, no responsibility about the manufacturing process. With that said, let me thank my students and all the team that work with me. These are my students during the 28 days test at ChipIR and ROTAX. And I'll be happy to take questions if you have any.
Thank you, Paolo, for a very interesting presentation. So let's see if we have questions. We have one in the chat.